Okay, internal flows. We're going to wrap up with internal flows today. And we will start with natural convection. That is an awesome topic because it's so widely seen and so present in our technologies. But to understand it, we need to go one notch up from what we have seen so far. Okay, so about the internal flows, let's wrap this up. We have here we go. So in internal flows, we have discussed that the main difference with external flows was that the two boundary layers touch each other, and therefore we had an entry length and a fully developed flow. And this fully developed flow had a constant Nusselt number, could be laminar or turbulent. For the case of it being laminar, we estimated that the Nusselt would be more or less four internal flows in a pipe of a circular section. And then we saw that depending whether it is the boundary condition, the pipe has a constant heat flux coming into the fluid, or if the pipe is at a constant temperature, we had slightly different Nusselt numbers, but they were around 4, right? In this case, 4.36 for uniform heat flux and 3.66 for uniform temperature. Then we also mentioned how we could extend our correlations, right? Now, not so, not coming out from an exact solution of a differential equation, but we could extend a formula of this type, right? That has a constant, so this is turbulent, but for laminar flow, in laminar flows, we have a constant Nusselt number, and we could extend our expressions by having this corresponding constant Nusselt number for different geometries. Now, the Nusselt number here is constant number, so it looks easy. However, we have to pay attention because Nusselt now is defined based on the hydraulic diameter. We have H, and this H is going to be the average convection coefficient over the perimeter of this pipe. K is the thermal conductivity of the fluid, and dH is the hydraulic diameter. And the hydraulic diameter is something that when you apply it to a circular pipe, it gives you the diameter of the pipe. But if the pipe is not circular, can be square, rectangular, triangular, can be many things. And in that case, what you do is you use this formula to calculate it. That is 4 times the cross-sectional area divided what is called the wet perimeter. So it's all the perimeter that is in contact with the fluid. In this case, it's very easy because it's these four sides here, these 4 sides here. In this case, that they say, oh, this is flat and very wide, so we only consider this the length of these faces. Same in this case, the length of these faces. These last two, the ones that are very flat and wide, they are very relevant because they are the type, they are the geometry that defines flow in a plate heat exchanger, in a compact heat exchanger. So both the circular sections typical of a shell and tube, and these other ones typical of a plate heat exchanger, those are going to be relevant and we're going to be using them. And so we, based on this hydraulic diameter, we can calculate a Nusselt number, and from there we can calculate a convection coefficient that is average over all this cross section. This is for laminar. Let's say we have a turbulent flow, and if we have a turbulent flow, now things get a little bit more iffy, but we still have a fighting chance. And this is what we are going to do. If we have a turbulent flow, first of all, using the hydraulic diameter, that with this expression here, let's get a proper pointer. Using the hydraulic diameter, we can calculate the Reynolds number. Then we check, is the Reynolds number bigger or smaller than 2300? If it is smaller than 2300, we use this table here that is also in the formula sheet I have uploaded. That in the formula sheet that I have uploaded. But let's say it's more than 2300. So we're gonna forget that there is a transition region and say, right after 2300, we're going to call it, for the purpose of this class, turbulent. And if it is turbulent, what we are going to do is use the correlations we have discussed before. Let me see. We are going to use this these correlations for fully developed flow, right? For example, the Ditus-Belter equation based on the hydraulic diameter. This is not going to be exact, but we have a fighting chance. Otherwise, we would have no idea what to do. So the Prandtl number, we're going to use the Prandtl we know, and the Reynolds number is going to be based on the hydraulic diameter. And this Nusselt would be the Nusselt that is the average of the perimeter, not necessarily the average on the length of the tube. This is average on the perimeter. So this is still a local Nusselt number. And this is the way we would do non-circular cross sections, whether it's laminar or turbulent. Let's do an example. So we started with this calculation example last class, in which we did the convection coefficient, calculated the convection coefficient in a pipe of 1 inch in diameter that is carrying water, right? And so we checked the Reynolds number, and we saw that the Reynolds number was below the critical Reynolds and was therefore laminar flow. Great. So we know what to use for the Nusselt number. It's going to be a constant number that depended on the boundary condition. And here they tell us that assume a constant surface temperature of the pipe. So that gave us a Nusselt of 3.66. We see it here too in the table. 3.66, we unpack it and we get H. Everybody's happy so far. We calculated the thermal and the hydrodynamic entry length, which you have already done. So we're good and we can keep moving. And then something you hadn't done is, in this example, let's calculate the average convection coefficient for the first meter of the tube. Now, they are asking us about convection coefficient in the entry length. Does anybody remember if in the entry length, the convection coefficient is higher or lower than in the fully developed flow? Anybody remembers if convection heat transfer is more intense at the entry or less intense at the entry, or the same? Anybody wants to say something in the chat? Okay, in the entry length, the boundary layers are developing and they are thin. So at the beginning, the heat transfer coefficient in the entry region is high and decreases, but doesn't decrease to 0. That would be the case, for example, of external flows. No, it decreases to a constant value and it stays. In the case, if we look at it from the point of view of Nusselt, it would decrease to something like 3.66 and stay there. But in the entry length is higher than that. And we have formulas for that. We have this complex slide here. But this complex slide told us something. that the average Nusselt in the entry region, if it is laminar, and we saw it's 2300, so the Reynolds number was below 2300, we can use either this formula or this other one. Both should give you more or less the same result. Now, if you're smart, and because the water has a Prandtl of 7, we fall in the region of this formula that says Prandtl bigger than 5. This is a formula I suggest you use. If instead of this formula, you somehow program in your computer this other one, this one is contained inside here. It's not exact, but it's pretty close, all right? And so this formula says we have 3.66, that is our fully developed value, plus something else that depending on the Grade's number. And we're not going to agonize about the Grade's number, other than here we have the expression, right? Is diameter over length, and they asked us about the first meter of pipe. So it's going to be the first meter of length, Reynolds, that depends on diameter, and Prandtl, that depends on the fluid. So let's see how we went about it. Here we have our formula, and we have first we have to calculate the Grade's number. D over X is diameter was 1 inch divided 1 meter. That is the length we care about. And the Reynolds 1194, which we had already calculated. Where was here is the Reynolds calculation of Reynolds, and the Prandtl number for water is 7, and we get these grades of 212.3. Something that is important to highlight. They ask us for the average convection coefficient in the first meter of the pipe. We should check that the entry length is longer than that. And entry length is something we had already discussed. And we have that the thermal entry length, where we have it, the thermal entry length was 10.61 meters, 10.6 meters. For sure, we are in the entry region. And once we got the Grade's number, we plug it into this equation here for Nusselt, and we get an average Nusselt value. Look, we get an average of 9.5. In fully developed flow is 3.66. The entry is super intense heat transfer. If the flow takes 10 meters to develop, for sure, I would consider making the tubes in this heat exchanger less than 10 meters. So we use all this entry region that has this enhanced heat transfer coefficient. Way downstream is not so good. So, okay. So we have calculated the convection coefficient for fully developed flow. We have calculated the entry length. We have calculated the average convection coefficient for an entry for the first meter that is within the entry length, right? We know so much. Nobody told us how long the pipe is in reality, right? But we would know if the pipe is less than 10 meters, we're in the entry length. If the pipe is much longer than 10 meters, that would be a crazy heat exchanger. Then eventually the fully developed flow conditions dominate. Let's change a little bit the question and say that if instead of 25 centimeter cubics per second, we have 250 cubic centimeters per second, we increase the flow by a factor of 10. What would happen? Right, just turn on the knob, and we're flowing 10 times as much fluid as before. The mean velocity is going to be 10 times higher. We calculated here we get almost 0.5 meters per second. And the Reynolds number in this condition would be almost 12,000. Definitely higher than the 2,300 that is the critical. So now we're talking about turbulent flow. Is from the point of view of the fluid, is a very different story. Before it was laminar flow, and we did all our calculations and we had some formulas that we understood. Great. Now we have turbulent flow. The heat transfer is enhanced by the advection that is related to the local motions of the turbulence, right? For example, in laminar flow, we don't have transverse velocities because everything is flowing in the direction of the pipe. But in turbulence, even although the fluid is moving in the direction of the pipe, the turbulence is enhancing the transverse heat transfer with those little turbulent motions, with that advection. So we're in turbulent flow, and we're gonna get the Nusselt number. How do we get the Nusselt number? Let's use the Dietz-Belter equation. And because in this case, what we are doing is, okay, so it will depend whether we're heating things up or cooling them down. So if we are heating the water, we would have an N of 0.4, and if we're cooling the water, we would have an N of 0.3. This difference in convection on the exponent of Prandtl is related to a pretty poor attempt to capture the changes in viscosity with temperature. And if you think when you're heating up, that means that the flow against the wall of the pipe is going to be hotter, therefore less viscous. And when you're cooling down, the flow against the pipe is going to be colder, therefore more viscous. So this changing in exponents is trying to anticipate what effect this temperature gradient is having on the boundary layer because of the changes in viscosity. So if we're heating the water, it was at room temperature, and we're heating it up, we would use an exponent of 0.4. And we go here. We use the exponent of 0.4. The Reynolds was to the 4/5, which we know is the typical Reynolds number for turbulent flow. We know this since we started our conversation on external flows on a flat plate. And we replace the values, and we get an H of 2100, 2000. Isn't this interesting? Before, we had an H that was a pathetic less than 100. And we said, once the fluid is developed in this laminar regime, there is no so much heat transfer coefficient because the gradient cannot develop anymore. In the case of turbulent flows, what we have is, what we have in this case, in the case of turbulent flow, we have that the local advection due to the turbulence enhances the heat transfer so much that now we have 2000. We would have called it everything 1000 before this class, right? And now we see, oh, in laminar, we have more or less 100, pretty sad. And in turbulent, we have 2000, right? The number 1000 we used before was kind of made up to be practical. But now we start to understand the subtleties. Oh, it depends on the Reynolds number and the turbulence, and you can calculate for each case something that is realistic, right? Much, much higher, 20 times higher, because it's turbulent. And this is all due to the advection that enhances the heat transfer. Okay, let's say it's turbulent, so let's calculate the hydrodynamic entry length in this turbulent condition. And in this turbulent condition, if you remember, the calculation for entry length said is more or less 10. The entry length in turbulent flow was 10 pipe diameters, right? And if it was 1 inch, now it's going to be, if the pipe diameter was 1 inch, now it's going to be 10 inches, right? 25 centimeters. Quite short, quite short. So if we decide that our heat exchanger was 1 meter long to take advantage of, we made the heat exchanger 1 meter long to take advantage of the thermal entry length in laminar flow. Now that we're in turbulent flow, we realize that who cares? It's pretty much all fully developed. And in any case, although it's fully developed, because turbulent heat transfer is so much higher, this is a much more desirable situation. So you guys know, heat exchangers tend to be designed to work with turbulent flow for the reasons that now become obvious. In a plate heat exchanger, for example, something interesting you get to see is that the plates are not flat, they are ribbed. And the reason they're ribbed is so these ribs trigger turbulence. Now, we're talking at a level that is beyond what we know in this class, because when in this class, we talk about parallel plates, we're talking about flat parallel plates. And what you're gonna see in a heat exchanger, and if we were to take the class in person, I have a heat exchanger that I always circulate where you get to see the ribs on the plate. And that triggers turbulent heat transfer. Okay, so let's calculate the hydrodynamic entry length. We did it here. And what if the tube had the same cross-sectional area, but is square? So the tube has the same cross-sectional area, so the mean velocity is going to be the same. But let's say that instead of being round, now it's a square, right? Which happens. And we can handle it, no problem. So we're talking about the 25 centimeter cubes per second and 250. Let's consider both cases. One we know is laminar. One was laminar for circular tubes, and the other was turbulent for circular tubes. It's likely to be the same. Let's check it out. Step number one, we needed to calculate Reynolds number. But Reynolds number depends on diameter, and when the cross-section is non-circular, so as you get to see here, we needed to use the hydraulic diameter, right? The hydraulic diameter that was 4 times the cross-sectional area divided the perimeter. For the case of a square cross-section, that would be the cross-sectional area is L square, where L is the side of the square, and the perimeter is 4L. And that gives us L, and we do this, L is the square root of the cross-sectional area, and here we have a hydraulic diameter of 2.25 centimeters. Based on that, we can calculate the Reynolds number, and we get 1,058. If you remember, before was almost 1,200. Now it's somewhere between 1,000 and 1,100, right? Somewhat similar. Whatever it is, we know we're in the laminar regime. So if we're in the laminar regime, we can use these numbers that we have here. We said that, let's assume the tube has this uniform temperature. So it was 3.66 for a round tube, but it's going to be 2.98 for a square tube. And guess what? Here we go. To get the Nusselt number, we have the 2.98 that came from this table times K, that it was the same as before for water, and the diameter. And the diameter is the hydraulic diameter, right? And the hydraulic diameter, and we get an H of 80. Very similar to what we had before, right? below 100. Laminar flow is not your friend for heat exchangers. If you want heat exchange, whether it's heat exchangers or anything else, you want turbulent. Conversely, if you want something that is insulating, you don't want turbulence, right? So these are things to keep in mind for us as engineers, that even before we do any fancy calculation, if we calculate the Reynolds number and we land in turbulent or in laminar, I don't need to do fancy math to realize that turbulent is going to be more or less 20 times more conductive than laminar. You see, different pipe sizes. Let's see the case of 250 meters per second, cubic centimeters per second. So now the Reynolds number is going to be 10 times higher. If we calculate this Reynolds, it's going to be 10,000 something. Turbulent again. How do we go about it? We use the Dietrich-Belter equation, but based on the hydraulic diameter. So we calculate things very much the same as before, except that the Reynolds is based on the hydraulic diameter, not in the diameter of a circle. This is a square now. And we get this Nusselt of 83. And when we back calculate H, we get 2200. Very similar to what used to be the round pipe again. So we see the difference between circular and square. It's not a big deal. Difference between laminar and turbulent is a huge deal. This value of H is an H that is not averaged through the length, but is averaged through the cross section. And by the way, because in turbulent flow, the Nusselt is constant, and the entry length tends to be short. This is pretty much the H you would assign to the whole pipe. So, if we wanted to account for the entry length, here we had seen the average Nusselt divided the Nusselt of fully developed, right? And as I mentioned, for long tubes, it's all the same. And for short tubes, we have this expression for which they did not give us in the book the value of C and M, but we know that the shorter the length considered, the higher the increase of Nusselt would be. Okay. So what we have just done, it looks like just going through formulas, but let's keep in mind, what have we done? We calculated the heat exchange, the convection coefficient for a pipe that was in laminar flow or turbulent flow, a round pipe. And we calculated also the entry length, and we calculated the difference in convection coefficient in laminar flow when between the fully developed flow and the entry length. And we saw it was quite big. The entry length was a lot better. And then when we saw the turbulence, the turbulent case, we saw that turbulent case so much better than even the entry length, right? From the point of view of a rate of heat exchange. And then we said, okay, what if instead of a circular pipe was a square pipe? We had a formula for that. And we did it both for the case of laminar and turbulent. And had I asked what happens if the tube is triangular, your answer would have been, no problem. Here is what I would do with a triangular tube, what we have in here. So briefly, I want to show you another correlation. And at this stage, people stop doing equations. They just use a functional form similar to what came from the equations, and they put coefficients and exponents that kind of make sense, that they are validated with experiments, but they don't calculate this from scratch again, the way we have done with the external flows with the boundary layer. So let's say now we have flow in concentric tubes. And this is a case, for example, of a concentric heat exchanger, concentric flow heat exchanger, right? There are heat exchangers such as these. They're not the most efficient, but they exist. They're commercially, they exist. So let's consider two cases. Let's consider one, the case in which one of these surfaces is insulated. For example, if we have this concentric heat exchanger and we are considering the flow in this annulus here, and all the outside part is insulated, right? Let's say all this is insulated. That's one case. Or let's say this area inside is not conducting heat, and the heat is conducted between the fluid and the outside, right? And they indicate here the Q double prime O is the heat flux with the outside, or Q double prime I, the heat flux with the inside. You choose one or the other. In this case, for table 8.2 here, if you choose heat flux outside, means inside is insulated. If you choose inside, means that outside is insulated. And each of these is going to have a Nusselt number attached to them. And here it tells us how if DI is 0, meaning it's a normal pipe, we go back to our 3.66, right? They are assuming the pipe is at constant temperature. So 3.66, this is the outside. But now if we say the inner tube, let's pick this one. The inner tube has a quarter of the diameter of the outer tube, right? If it is insulated on the outside, if this part outside is insulated and we're exchanging heat between this inner part and the fluid, we would be using this Q double prime I, and it's based on Nusselt I. And we would use this Nusselt number. If instead the inner pipe has a quarter of the diameter of the outer pipe, right? But and this is insulated on the inside, the heat exchanger would be with the outside, and we would use the Nusselt of the outside. An interesting thing here, what if the two pipes have pretty much the same diameter, right? Such that it's just such a narrow slit through which the fluid flows. No problem. And you know what the solution is? They send us, when they say this is so thin, essentially, although it's an annular cross-section, it's so thin that it's the same as if it was a flat cross-section. And what do we look? We look table 8.1, right? This one here, B over A equals infinity, right? And for uniform temperature, this 4.86, whoops, is what appears here, 4.86. Is what appears here, 4.86 for uniform temperature and insulated on one side and heated on the other. Check out this, how cool, because this made sense. We do not have formulas, right? And if we wanted to have the case of, if we, instead of constant surface temperature, they told us constant heat flux on one side is insulated, we would know that instead of a 4.86 here, we would have a 5.39. The number is not all that different. Here's where the understanding comes, right? The book didn't tell us, but we know that when the annulus becomes so thin, we are back to something flat, and we can extrapolate to things that the book didn't tell us, because we know, because we understand what we are doing. I think it's pretty cool. There is another case the book discusses, that is the case in which you have a uniform heat flux on both surfaces. So now this is kind of a lot more complex from the point of view of a plug and chug, but we are imposing a Q double prime O, that is a heat flux on the outside. We are imposing a Q double prime I on the inside. We're imposing those constant heat fluxes. So how do we calculate the Nusselt inside, right? We would get this Nusselt II, right? And divide by 1 minus this ratio of the heat fluxes, which we know because they're imposed, and this theta asterisk. Now, what these two things are, let's not worry too much, other than we know where to go. We go to this table, and it says, depending on the ratio of diameters, I have this Nusselt II that I would plug in here, and this theta asterisk 1, I would have it in this column. This way, we can calculate the heat flux when we have the Nusselt number inside or the Nusselt number outside for the case of an annular tube, which has imposed heat fluxes. And the heat flux could be 0, and that means the tube is insulated. So are these slides on a different PDF? No, these slides are in the book. These slides are in the book. I think they're not in the notes, but I wanted to share this with you. No. Let's see. What I'm going to do is upload these slides separately as a PDF too, so everybody has them too. But they are all in the book. I'm going to upload them as a PDF. Okay, good. So good for internal flows. We can calculate pretty much everything, and this is for an annulus in with laminar flow. If the flow was turbulent, what we do is we calculate the hydraulic diameter. The only thing that is interesting in this case of the annular flow is that to calculate the hydraulic diameter, we have to calculate the cross-sectional area of the annulus and the perimeter. The perimeter is the sum of the perimeter of the outer pipe plus the perimeter of the inner pipe, because both sides are wet now. The outside is wet and the inside is wet. So in this case, the hydraulic diameter uses a perimeter that is the sum of both perimeters. That's the only difference. Good. So I'll keep looking at the chat as I move on to get into natural convection, our next stop.